Hi, I'm Aditya and I'll be presenting our work PhISH-Net, which is a physics-inspired system for high-resolution underwater image enhancement. The goal of this work is to recover lost colors in images captured underwater for enhancement and reconstruction. This can also aid as a pre-processing step for high-level vision tasks such as object detection, tracking, and segmentation. Early works didn't really consider the physical process of underwater image formation, which led to models such as the underwater image formation model being developed. But methods using these models are image specific and are computationally expensive to run. So recent studies using deep neural networks generalize well, but they process these high resolution images at much reduced resolutions. So before I explain the proposed method, let me give you a quick background on the underwater image formation model. So any image I captured underwater can be modeled using two components, which is the direct signal D and backscatter B. These terms are governed by two coefficients, which are the wideband attenuation and the backscatter coefficient respectively. So this equation can be expanded as follows. So the idea is to first estimate this backscatter B. And using this we can obtain this direct signal D, which we can then enhance. So to estimate the backscatter, we follow an algorithm inspired by the dark channel prior, where we search the regions of the input image where the scene reflectance or the illumination tends to 0. So we modeled an estimate of the backscatter using this equation and estimate the four coefficients using a non-linear least square fit based on algorithm 1, based on which we can obtain the backscatter at any depth z. And as you can see, all of the equations described previously also depend on the depth z. So it is important to first estimate depth, for which we use a boosted version of a monocular depth estimation technique. Mainly we use a base model of MIDAS without retraining to generate accurate depth maps. Moving on, the estimated direct signal is often dimly lit, and enhancing it mimics the low light image enhancement problem. Thus, we impose PhISH-Net to learn an image to a 3-channel illumination mapping, and based on the retinex model, the enhanced image is given by the ratio of the illumination map to the input direct signal, and epsilon is a stabilization constant. And the network also uses a bilateral grid-based upsampler. So most of the network computations are done at a much reduced resolution, which makes it computationally efficient. And PhISH-Net is optimized to predict the illumination map by minimizing 3 main losses, which are the image reconstruction loss, the color loss, and a smoothness loss. Additionally, we also impose a novel prior on the wideband attenuation coefficient based on experimental findings in literature. Finally, to eliminate any undesirable color casts, we employ a photo finishing step which uses white balancing and color correction mainly in the red and blue channels. So the proposed framework is as follows. First, we estimate the backscatter B, using which we obtain the direct signal D, and a reduced resolution version of this direct signal is passed to an encoder which predicts the coefficients for this attenuation prior, which is also passed to a bilateral grid-based upsampler which finally predicts the illumination map S. And the stage-wise results are shown here. This is the original input I, and this is the backscatter removed version D, and this is the final enhanced image I. So here are some results on the UIEB dataset, the SQUID dataset, and the UVP dataset. Here's also an example for a downstream tasks where we try to evaluate shift features on the image. As you can see that the input image only provides 60 key points, whereas an enhanced version of this image provides almost 1200 key points. Moving on, we run ablation on the various losses used, and as you can see, both metric wise and visually, using all the 4 losses yields a much better result. And we've also seen the impact of photo finishing, where most of the metrics seem to improve upon using photo finishing. Finally, the method is extremely lightweight at only 0.55 million parameters and 0.09 gigaflops, and the runtime of the network is also very low. Most of the runtime goes in the pre and post processing steps, so future work can look into reducing the time in pre and post processing. Thank you.